This paper explores the fabrication of metal nanowires using DNA-templated metallization, focusing on a novel approach to achieve sequence-specific metal deposition for nanostructure construction. Metal nanowires have important applications in nanoelectronics due to their unique electrical properties and nanoscale dimensions. The main challenge is to control metal deposition at the nanoscale with high precision and selectivity. The approach taken here utilizes DNA triblock copolymers synthesized enzymatically to create specific sites for metal binding and deposition. By exploiting DNA sequence specificity and chemical interactions, the authors aim to fabricate linear metal nanowires and nanogap electrodes with precise control over metal placement. Key to this method is the selective binding and reduction of cisplatin to guanine-rich DNA sequences, resulting in localized platinum nanowires, while modified DNA blocks form nanogaps that function as electrode gaps. This biometallization strategy builds upon previous work on DNA metallization with silver, extending it to sequence-specific platinum deposition using DNA triblock copolymers. The paper presents the synthesis, characterization, and metallization processes, demonstrating the potential for constructing novel nanoscale tunneling structures and conductive nanowires using DNA as a template. Overall, this work merges genetic polymer chemistry with nanofabrication techniques to address challenges in precise nanoscale metal patterning. Figure 1 illustrates the fabrication process of metal nanowires using DNA-templated metallization with DNA triblock copolymers. The approach begins with the synthesis of DNA triblock copolymers composed of poly-DG, poly-DC, and poly-7-deazid-DG, poly-DC blocks by enzymatic polymerization using the Klenau fragment exo-DNA polymerase. This triblock design is critical because the poly-DG, poly-DC segments selectively bind cisplatin, while the poly-7-deazid-DG, poly-DC segments do not, due to the substitution of N7 in guanine with carbon in 7-deazoguanine, preventing cisplatin attachment. The DNA polymers were synthesized from DG10 and DC10 primers, resulting in polymers approximately 3,000 base pairs long, as confirmed by electrophoresis. Next, these DNA polymers were immobilized on mica substrates via the Langmuir-Blodgett method, and then treated with cisplatin, which selectively binds to the guanine-rich segments. Reduction of the bound cisplatin produces selective platinum deposition on poly-DG, poly-DC blocks, forming platinum nanowires, while leaving the 7-deazid-DG blocks free, effectively creating nanogaps. Atomic force microscopy, AFM, measured the height changes, confirming that one DNA block's height increased after platinum deposition, indicating successful, selective metallization. This sequence-specific metallization approach extends previous methods using silver and allows precise control of metal localization on the DNA scaffold for constructing nanoscale tunneling electrodes and conductive nanowires. The authors interpret these results as clear evidence of how DNA sequence manipulation can direct metal nanowiring with selectivity and nanoscale precision. In summary, this study demonstrates an innovative approach to fabricate metal nanowires with nanoscale precision using DNA triblock copolymer templates and sequence-specific metal deposition. By synthesizing DNA copolymers containing selectively modifiable guanine blocks alongside non-binding 7-deazoguanine blocks, the researchers achieved selective binding and reduction of cisplatin to form platinum nanowires confined to specific regions of the DNA polymer. This process creates nanogap electrode structures, where platinum nanowires are separated by non-metallic DNA segments, a critical feature for applications in nanoscale tunneling devices and nanoelectronics. Atomic force microscopy confirmed the selective metallization and revealed height differences corresponding to platinum deposition, validating the success of their templated approach. This work advances the field of biometallization and nanofabrication by providing a method to control metal placement at the molecular level using enzymatically crafted DNA sequences as scaffolds. The ability to engineer conductive metal nanowires with precise gaps lays foundational groundwork for future nanoscale electronic components, sensors, and novel tunneling junctions. The authors interpret these findings as a significant step toward integrating biological molecules with advanced electronic nanostructures, opening pathways for designing customizable and sequence-specific nanodevices in bottom-up nanotechnology.